Imagine this. You're going to die. Not today, not tomorrow, but in a few decades, for sure. And here's the strange part. From the standpoint of physics, this is perfectly normal. The universe has no objection. In fact, it has been doing exactly this for billions of years, creating stars and destroying them, building galaxies and tearing them apart. You are just a tiny ripple in this endless process. But here is a question that has haunted the greatest minds on the planet for thousands of years. Where did this universe even come from? Who or what set it in motion? When did it happen? And above all, will it ever end? In 1988, a book appeared that sold more than 10 million copies in 40 languages. Written by a man who could neither move his hands nor speak without a voice synthesizer. His name was Stephenhawking. The book is called A Brief History of Time, From the Big Bang to Black Holes. A book about the most fundamental things, how the universe works, written without a single unnecessary equation. Almost without a single one. Today we will travel this entire journey together. From the turtles that hold up a flat world to black holes that evaporate. From the Big Bang to the arrow of time. From the uncertainty principle to the dream of unifying all of physics. And by the end, you will understand something important, not only about the universe, but about what human beings are truly capable of. Subscribe so you never miss a book that genuinely changes the way you think. No filler in 30 minutes. A long time ago, a well-known scientist, said to be Bertrand Russell, gave a public lecture on astronomy. He explained how Earth revolves around the sun, and the sun around the center of our galaxy. When it ended, a small elderly woman rose from the back row. "Everything you said is nonsense. The world is actually a flat plate resting on the back of a giant turtle." Smiling condescendingly, the scientist asked, "And what does the turtle stand on?" "You are very clever, young man," she replied, "but it's turtles all the way down." Most of us find that amusing, but Hawking poses an uncomfortable question. Why do we think we know better? How much more reliable is our picture than a tower of turtles? People have been constructing pictures of the universe for millennia, only to have them collapse. Aristotle believed Earth was the center, with all celestial bodies revolving around it in perfect circles. It seemed obvious. The sun travels around us. Look up and see for yourself. In the 2nd century, Ptolemy developed a complex system, Earth at the center, surrounded by 8 spheres, the moon, the sun, the 5 known planets, and the outer sphere of fixed stars. Planets moved in small circles within larger circles, explaining their strange paths across the sky. The system worked. It predicted planetary positions. The church accepted it as truth. It seemed the question was settled forever. Then came Copernicus, a Polish cleric who quietly, at first even anonymously, proposed a different model. The sun at the center, Earth and the other planets revolving around it, considered heresy. Galileo, who supported Copernicus and proved him right with the newly invented telescope, ended up on trial and was forced to publicly renounce his views. They say that as he rose from his humiliating kneel, he muttered, "And yet it moves." But truth cannot be stopped. Kepler showed planets move in ellipses, not circles. Then Newton arrived with his theory of gravity, a universal law explaining both a falling apple and planetary motion with the same formula. A triumph of reason. It seemed like everything was finally understood, but no. Tell me in the comments, what is the strangest scientific idea you have ever come across? One that first seemed absurd and then turned out to be true. It will be interesting to compare with what comes later in this video. In 1905, a young patent clerk from Bern published several papers that turned all of physics upside down. His name was Albert Einstein. The special theory of relativity shattered the idea of absolute time and absolute space, which had seemed self-evident since Newton. Newton believed that time flowed the same everywhere for everyone. A second is a second, regardless of where you are or how you move. Einstein proved otherwise. The speed of light in a vacuum, about 186,000 miles per second, is the same for every observer regardless of their motion. And this simple statement changes everything. Imagine you are on a train throwing a ball forward at 10 miles per hour. Someone on the platform sees it moving at train speed plus 10. Now replace the ball with a beam of light. By classical physics, light speed plus train speed. But no, The speed of light is exactly the same for the platform observer as for you in the car. For this to be possible, time for a moving object must run slower, and space must contract. Not a metaphor, a reality confirmed by experiment. Clocks on fast aircraft and GPS satellites genuinely run differently than clocks on the ground. Without correcting for this, your navigation app would send you to the wrong place. 10 years later, Einstein created general relativity. Gravity, he explained, is not a force in the conventional sense. It is the curvature of spacetime caused by mass. Earth orbits the sun not because the sun pulls it at a distance, but because the sun's mass warps space around it, like a heavy ball on a rubber sheet. Earth moves through that curved space along the shortest available path, which looks like an orbit. I remember when I first read about this, it knocked me sideways. We tend to think of space as emptiness, an empty box in which events take place. But space itself is flexible, alive. It responds to matter. Matter tells space how to curve. Space tells matter how to move. That was a revolution. Now the next step. If space curves under the influence of mass, what happens to the universe as a whole? At the start of the 20th century, most scientists believed the universe was static, always as it is, always as it would be. Einstein himself believed this, and even added a special cosmological constant to his equations to balance gravitational collapse and produce a static model. He later called that his greatest blunder. Because in 1924, astronomer Edwin Hubble made a discovery that changed everything. Observing distant galaxies, he noticed something odd. Their light was shifted toward the red end of the spectrum, redshift. It occurs when a light source moves away from the observer, like the pitch of a siren dropping as a car recedes. Hubble understood. All distant galaxies are moving away from us, and the farther the galaxy, the faster it recedes. The conclusion was staggering. The universe is expanding, and if it is expanding now, then in the past it was smaller, far smaller. If you mentally rewind the film, everything converges to a single point, a point of infinite density and infinite temperature. That is the Big Bang. The moment everything began, space, time, matter, energy. It happened approximately 13 to 14 billion years ago. Here is what those first moments looked like. In the first second, the temperature was around 10,000 billion degrees, 1,000 times hotter than the core of the sun. The universe was a primordial soup of photons, electrons, neutrinos, protons, and neutrons. Within 3 minutes, temperatures dropped enough for nuclear fusion. Protons and neutrons fused into helium nuclei. Roughly 1/4 of all matter became helium, 3/4 remained hydrogen. We observe that ratio throughout the universe today, directly confirming the Big Bang. About 380,000 years later, temperatures fell to a few thousand degrees. Electrons slowed enough to attach to nuclei, forming the first atoms. The universe became transparent to photons. They were finally free to travel unimpeded. That stream of photons has survived to this day. We call it the cosmic microwave background radiation. It was discovered by accident in 1965 by American physicists Penzias and Wilson, who were trying to track down interference in a radio antenna. They detected a faint, uniform signal coming from every direction in the sky. It was the echo of the Big Bang. For that discovery, they received the Nobel Prize. And this discovery carries a radical implication. The universe had a beginning, which means it may also have an end. But what was there before the Big Bang? Hawking says the question is meaningless. Time itself came into existence at the moment of the Big Bang. Asking what came before is like asking what lies south of the South Pole. Nothing. It is the boundary of the very concepts of where and when. Has it ever happened to you? You read something about physics, and your mind just reels at how strangely reality is constructed? Write in the comments which idea hit you hardest. Now let's move into the quantum world, and this is where things get genuinely strange. In 1927, the German physicist Werner Heisenberg formulated the uncertainty principle. It states this: you cannot simultaneously know both the exact position of a particle and its exact velocity. The more precisely you determine one, the less precisely you can know the other. And this is not a limitation of our instruments. It is not a problem of technology. It is a fundamental property of nature itself. What does this mean in practice? It means that determinism, which seemed obvious since Newton, the idea that if you knew the exact state of every particle today, you could perfectly predict the entire future, is an illusion. Nature is fundamentally random at the quantum level. Not because our measurements are poor, but because the particle simply does not have a definite position and a definite velocity at the same time. These are two incompatible states. Quantum particles behave in ways completely unlike anything we encounter in everyday life. A particle can exist in multiple states simultaneously. This is called superposition. It can pass through a barrier that should have reflected it, quantum tunneling. It can be entangled with another particle billions of light years away, so that measuring one instantly affects the state of the other. None of this is science fiction. It has been confirmed by thousands of experiments. Quantum mechanics is what makes the transistors in your smartphone work, along with lasers and MRI scanners in hospitals. And yet, quantum mechanics and general relativity are fundamentally incompatible with each other. These are the two pillars of modern physics, each working with extraordinary precision in its own domain, but together they produce mathematical contradictions. Unifying them is the central challenge of theoretical physics. It was the challenge Hawking devoted his entire life to. There is one more concept from the quantum world that shatters intuition. Schrödinger's cat, a thought experiment where a cat is sealed in a box with a poison mechanism triggered by a random quantum event. While the box is closed, quantum mechanics says the cat is simultaneously alive and dead, a superposition of two states. Only when we open the box does the wave function collapse into one definite outcome. Most physicists believe superposition is real for particles, but does not manifest at the scale of cats due to decoherence. But whether observation affects reality at a fundamental level remains a genuinely open philosophical question. Now let's talk about elementary particles. What is everything around us made of? The Greeks thought it was four elements: earth, water, fire, and air. Then atoms. Then it turned out atoms are divisible, a nucleus of protons and neutrons at the center, a cloud of electrons around it. Then protons and neutrons themselves proved divisible, made of even smaller particles called quarks. Today, physics describes matter through the Standard Model. 6 types of quarks bind together into protons, neutrons, and other particles. 6 types of leptons, the electron belongs here. Plus the force-carrying particles, photons for electromagnetism, gluons for the strong nuclear force, and W and Z bosons for the weak force. These interactions correspond to the 4 fundamental forces of nature. Gravity is the weakest, but acts over any distance and always attracts. It keeps planets in orbit and shapes large-scale cosmic structure. Electromagnetism holds atoms and molecules together, everything we are made of. The strong nuclear force keeps quarks inside protons and protons inside nuclei. Without it, atoms would fall apart. The weak nuclear force governs radioactive decay, converting neutrons to protons, ultimately heating Earth's interior and making life possible. The beauty of physics is that these forces are different expressions of something unified. Physicists already combined electromagnetism with the weak force in 1968. Grand unification would add the strong force. Quantum gravity would then bring in everything else. That complete theory does not yet exist, but we are searching. And now, the part many people pick up this book for: black holes. The term was coined in 1969 by physicist John Wheeler, but the concept appeared much earlier. In 1783, Cambridge lecturer John Michell reasoned, if a star is massive and compact enough, its gravity will be so strong that not even light can escape. The star would be invisible, absorbing all light that reaches it. That is a black hole. How does a black hole form? A star is a balance between 2 forces, gravity pulling gas toward the center, and the pressure of thermonuclear reactions in the core pushing outward. For millions and billions of years, the star burns. Hydrogen converts to helium, helium to carbon, carbon to heavier elements. But at some point, the fuel runs out. Pressure drops. Gravity wins. The core begins to collapse. If the star's mass is large enough, more than roughly 3 solar masses, Nothing can stop this compression. Matter collapses to a singularity, a point of infinite density. Around it forms the event horizon, the boundary beyond which nothing can return. Not light, not matter, not information. The distance from the center of a black hole to the event horizon is called the Schwarzschild radius. For an object with the mass of the Sun, it would be roughly 1¼ miles if the Sun were somehow compressed to a single point. What happens to someone falling into a black hole? For an outside observer, time for the falling object slows and effectively stops at the event horizon. They will never see it cross, it just grows redder and dimmer, freezing in place. For the person falling, nothing special happens at the boundary of a large enough black hole. They simply keep falling. Only later do tidal forces, the difference in gravity between head and feet, begin to stretch and tear them apart. What makes black holes even stranger is that inside the event horizon, the roles of space and time are reversed. Outside, you can move through space in any direction, but time always moves forward. Inside the event horizon, the movement toward the singularity becomes just as inevitable as the passage of time outside. The singularity is not a place in space, it is a moment in time, and it cannot be avoided any more than you can avoid the next second. We read so you save hours. If you want more breakdowns like this, support the channel. Thank you for watching. Now, Hawking's most astonishing discovery, the one that made him truly famous in the scientific world. In 1974, Hawking applied the principles of quantum mechanics to the event horizon of a black hole and found something completely unexpected. Black holes are not so black after all. They radiate. Here is the mechanism. The uncertainty principle says, in empty space, pairs of virtual particles, particle and antiparticle, constantly spring into existence, stay together a fraction of a second, then annihilate as if they had never been. Normally, this process is invisible. Energy is borrowed from the vacuum and returned immediately. But at a black hole's event horizon, something different happens. One particle of the pair can fall across the horizon, while the other escapes into space. To conserve energy, the black hole pays for the escaping particle with its own mass. The black hole's mass decreases. This phenomenon was named Hawking radiation. A black hole slowly evaporates. Small black holes evaporate faster. Large ones evaporate with inconceivable slowness. For a black hole the size of the Sun, this would take a time incomparably greater than the current age of the universe. But in principle, they are finite. This discovery was revolutionary in several ways at once. For the first time, quantum mechanics and general relativity were united in a real, testable prediction. And it raised the deepest question physicists have not yet resolved. Where does the information about objects that fell into a black hole go once the hole has evaporated? Quantum mechanics says information cannot be destroyed, but if the black hole disappears, taking everything with it, where does the information go? This is the information loss paradox, one of the great open questions of theoretical physics. Personally, that paradox grabbed me more than anything else, because it shows we know precisely that there is something important we do not know. And that, it seems to me, is the true beginning of science, honestly admitting where understanding ends. Now, to what Hawking thought about the fate of the universe itself. We know it is expanding. Will that continue forever? It depends on how much matter the universe contains. If enough, gravity eventually slows the expansion and the universe collapses. Billions of years later, the Big Crunch, a mirror image of the Big Bang. If not enough density, expansion continues forever. Galaxies scatter, stars go dark, black holes evaporate, and what remains is a cold, dark, infinite emptiness. But Hawking proposed something more radical, the no-boundary universe. Together with Jim Hartle, he developed a model in which the universe has no singular starting point. Using imaginary time, spacetime turns out to be closed, finite, but without edges or beginning. Like the surface of the Earth, finite area, but no edge to fall off. The universe could have existed without a moment of creation, with no boundary in time. Hawking once presented this idea at a conference in the Vatican. The Pope told the assembled scientists that they were welcome to study the evolution of the universe after the Big Bang, but not the moment of creation itself, as that was a divine act. Hawking later said with a smile that he had been quite relieved the Pope did not know what his paper had actually been about. Now let's talk about the arrow of time. Why do we remember the past but not the future? Why does a broken cup not reassemble itself? The laws of physics are symmetric in time. The equations work equally well in both directions. A recording of two particles interacting, played in reverse, also looks physically valid. But real experience is not reversible. We never see a cup gather itself back up off the floor. Hawking speaks of three arrows of time, all pointing the same way. The first, thermodynamic. Disorder in a closed system always increases, the second law of thermodynamics. A cup shatters, the reverse never happens in practice. The second, psychological. We remember the past, not the future, a consequence of the first, since recording information itself increases disorder in the universe. The third, cosmological. The universe expands rather than contracts. All three arrows point in the same direction, and Hawking shows this is not a coincidence. We live in the expanding phase of a universe that began in an extraordinarily ordered state. It is precisely that ordered beginning which sets all the other arrows of time. If the universe had started in equilibrium, there would be no direction of time at all. No memory, no life, none of us. And finally, the dream of the grand unification. We have general relativity. It describes large scales, gravity, spacetime. It predicts planetary trajectories, the expansion of the universe, the existence of black holes. We have quantum mechanics. It describes small scales, particles, fields, interactions. Both theories work with stunning precision in their respective domains. But in the places where both are needed simultaneously, at the moment of the Big Bang, inside a black hole, physics breaks down. It gives nonsensical answers. It says infinity where it should give a number. This means both theories are incomplete. One of the leading candidates is superstring theory. The idea: fundamental particles are not point-like objects, but tiny vibrating strings of energy. Different vibration modes produce different particles, like one string bowed different ways, producing different notes. Superstring theory requires more than 3 spatial dimensions, in some versions 10 or 11. The extra dimensions are curled at scales so tiny, around the Planck length, that we simply don't notice them. And perhaps never will. Have we found it? No. Hawking wrote with cautious optimism, it seemed we were close. But today, nearly 40 years after the book appeared, no complete theory of quantum gravity exists. We are still searching. And that is one of the most thrilling things about science. The frontier of the unknown is always somewhere ahead. Hawking closes his book with words worth hearing. If we do find a complete theory, it will not be a victory only for scientists in white coats. It will change the thinking of ordinary people. Because that theory will tell us why the universe exists, why we exist, and why there is something rather than nothing at all. And that will be the greatest triumph of human reason. There is something that did not make it into the dry summary, but without which the picture is incomplete. Hawking learned of his illness at 21, and the first few years after the diagnosis were the hardest of his life. He was depressed. He drank. It seemed there was no point in going on. Then he met Jane Wilde. They married and had children, and something changed. In his memoir, he wrote that the illness, strangely enough, had set him free. Before the diagnosis, he had been drifting without real purpose. Afterward, every year felt like a gift. He worked with a ferocity that healthy people rarely manage. In '85, Hawking contracted pneumonia, and doctors suggested his wife take him off life support. She refused. After the tracheotomy, he lost his voice. A California company built him a program. Using a small switch, he selected words on a screen. A synthesizer read them aloud. Around 15 words per minute. In that language, he wrote A Brief History of Time. In that language, he lectured to the world. Stephen Hawking spent more than 50 years in a wheelchair. Motor neuron disease, amyotrophic lateral sclerosis, was diagnosed when he was 21. Doctors gave him 2 to 3 years to live. He lived to 76. Over those years, he lost first the ability to walk, then to speak, then control of nearly his entire body. In his final years, he communicated through a single cheek muscle, raising an eyebrow to activate a switch. 1 word per minute. And in those very years, he wrote a book that became a global bestseller, discovered Hawking radiation, developed the no-boundary theory of the universe, and lectured on the most prestigious stages on Earth. He proved not only how the universe works, he proved that the ability to think is the one thing no illness can take away. This book is not simply a physics textbook. It is an invitation to ask the biggest questions. Where did the universe come from? Where is it going? What is time? And why does anything exist at all rather than nothing? Hawking does not offer final answers. He honestly acknowledges where understanding ends. But he shows us how to think, how not to fear questions that have no answers yet. And that, perhaps, is worth more than any ready-made answer. One more thought worth carrying with you. Hawking did not write this book for physicists. He wrote it for all of us. For those who look up at the night sky and wonder what is out there. For those who sense that the world runs deeper than it appears at first glance. He believed that any ordinary person is capable of understanding how the universe works, if it is explained clearly and honestly. And in that sense, A Brief History of Time is not simply a book about physics. It is a book about human curiosity, about the fact that asking questions is itself a great thing, about the fact that not knowing is not a weakness, but a starting point. If you enjoyed this video, like it and subscribe so you do not miss the next book. Every week, a new summary that changes how you see the world. Burning books is a crime, but not reading them is even worse. We fix that in 30 minutes. Subscribe.